Hello.
Hello? Yeah. So should I start? Yeah. Okay. Okay. Welcome everybody. I'm really happy and really proud that this workshop is happening here. For those who, for those, for those who sort of have an incomplete idea of the point of this workshop is, for me, really exciting. I mean, all of you probably know that in fundamental physics you have sort of theorists doing, here is my 20-dimensional space with 5 supersymmetries and whatever else, and experimentalists are working on things that theorists fundamental physics-wise on gravitational waves and the Higgs, which are things that are theoretically established for decades. And this is, for most people, considered to be the greatest crisis in modern fundamental physics. In my humble opinion, what we'll be discussing about this week is maybe the most promising way of getting out of this in most of our professional lifetime. There is really, I mean, the idea what particle physicists call 10 to the 19 GeV, everybody else calls 1 milligram and maybe 1 microgram, and maybe there is ways to access this scale in quantum effects of this at this scale experimentally, which are actually technologically feasible. And the experimental proof of this is that most of this audience is experimentalists who are not just saying, yeah, right, in your dreams, but actually preparing for this and sort of making preparations for this eventuality. That to me is really exciting. I mean, of course, as with everything, it's a gamble, but it's the fact that you are here is basically means that you have the hope that something very interesting is going to come out of this in the next decades, and it is worth discussing what these sort of experiments will really lead to. And I really hope that the spirit of the workshop is this. This will be a discussion between theorists and experimentalists about how quantum effects of gravity might be accessible in the laboratory. Okay, for any logistical local things, we are here. We are here. Please feel free to ask. Please feel free to ask anything.
Yeah, you have Umberto around, you have Tiago around, so any couple of questions you might direct them to them as well. Right, guys?
Yeah. And now, should we start?
Yeah, and welcome to São Paulo, guys. Hope you guys have fun.
Yeah.
And we have to pass a couple of videos right now about the institute here and the ICTP-SAIFR, and after that we'll start our very first talk. So, let's go.
O Instituto Principia é um centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o You Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Okay, and now we are starting the scientific part of this event, and our first presentation will be by Professor Markus Aspelmeyer from Vienna, and he will talk about quantum sources of gravity, why and how, and mostly how. Please.
Thank you very much. It's a real pleasure to virtually be here. I sincerely apologize for not being able to come. It turns out we do have the 20th anniversary of our very own quantum center, the Vienna Center, the Institute for Quantum Optics and Quantum Information of the Academy of Sciences. And so I basically have to be here in Vienna to celebrate this one. So, but I do hope for some virtual discussions and to learn something in that way. Now, my talk, as you can see from the title, essentially addresses the question, where are we with experiments? And before I go there, let me start with an historical excursion into another field that will certainly be relevant for our discussions, namely the quantum control of massive objects. And one of the inspirational works on that dates back to Erwin Schrödinger in 1931. So this is a famous letter that Schrödinger wrote back then to Sommerfeld, in which he discusses how he says, a tormenting fundamental question. And what he describes in his letter to Sommerfeld is a situation where you see here this thought, a photon, a Lichtquant, so a quantum of light, is interacting with a heavy mirror. It says here, schwerer Spiegel. So, and he describes in his letter the way those two systems interact and how then you can use measurements on the mirror to learn something about the properties of the photon. And all of that goes, of course, vice versa. And essentially, if you dig a little bit into this letter, he gives a correct quantitative analysis of what we know today as continuous radial entanglement, namely that the momentum and position of the photon are imprinted on this mirror in such a way that the accuracy, the product of the accuracies of those two values can be pushed way below the limit of Planck's constant. And we know this is a quantitative statement for entanglement where the product of the conditional variances goes below h bar. And so this is an instance of optomechanical entanglement, which paved the way, I would say, in a sense, to understanding how we can actually control quantum states of massive objects, here the center of mass degree of freedom of a heavy mirror, by employing the quantum properties of light that it interacts with. Then basically, well, this was 90 years ago, but then 90 years, or let's say 70 years later, what had happened was essentially the microfabrication effort suddenly allowed to produce mechanical and optical systems in a regime where they became sensitive to radiation pressure effects. And in combination with optical or microwave cavities, and these are ideas that have been very much pioneered by Vladimir Braginsky in his early thoughts and early works about gravitational wave detectors, you can now couple a mechanical system to an optical or microwave cavity resonator. And what essentially happens is that when you pump this cavity detuned, so the frequency of your pump is detuned with respect to the cavity frequency, you get forces, radiation pressure forces on your mechanical system that depend both on position and on the momentum of the system. And that means what you get now is you get a beautiful way how to act on the full susceptibility of this mechanical system, so on the real part and the imaginary part, namely the spring constant and the damping, and all of that in a fully quantum framework. So you can use now quantum states of light to actually start to control quantum states of the mechanical system. And this universal coupling mechanism of radiation pressure effects on a mechanical center of mass degree of freedom coupled to an optical or microwave cavity covers essentially 20 orders of magnitude in mass and can be used to produce non-classical states of motion. Let me just historically give you one example from the Vienna lab. So what we did was we basically created, you see here, a tiny cantilever structure that was made out of optical coating alone. So we basically just microfabricated these little structures on top of a half-inch Thorlabs mirror. And then we under-etched the whole system such that this is now a freestanding structure only consisting out of high reflectivity coating. If you then use that as the back end of a Fabry-Perot cavity, you see this is a Team 00 mode of the Fabry-Perot cavity. You can have now radiation pressure on this tiny cantilever, and by detuning now the laser that drives the cavity, you can actually start to cool the center of mass motion, because what happens is with the detuning, you have the light that is scattered from your tiny mirror here has both Stokes and anti-Stokes component in a Raman scattering process. So you have frequencies of photons that are scattered inelastically that either take away energy of the system, so meaning they are then at higher frequencies, or deposit energy of into the system, which means the scattered photons have less frequency, which would then be a Stokes scattered photons. And if the anti-Stokes scattered photons, which take away energy of your center of mass degree of freedom, are resonant with the cavity, you have resonant enhancement of the anti-Stokes scattering process, which is also known as sideband resolved laser cooling of mechanical motion if your cavity line width is much smaller than your mechanical frequencies. And that way, what we have achieved over the years, so we started out with moderate cooling of 2 orders of magnitude of the center of mass degree of freedom. Then we improved the quality of the mechanical systems, because the heating rates through mechanical dissipation typically very quickly led to an equilibrium that did not allow ground state cooling. And eventually we teamed up with Oscar Painter's team at Caltech, who pioneered this fantastic optomechanical crystals, where you have a 1D photonic crystal waveguide that is freestanding, such that the electromagnetic field modes are co-located with the mechanical displacements here at high frequencies, leading to high optomechanical interaction. And then eventually this allowed us to ground state cool the system with laser cooling. And then over the years, we placed the whole thing into a dilution refrigerator. And this was basically the starting point to start off with a mechanical system in a ground state, and then achieve single phonon control by controlled single photon post-selected interaction. But I don't want to go into the details here. Suffice to say, where we are right now on a global scale is that we have many, many experiments from many groups all around the world that demonstrate beautifully how we can now prepare mechanical systems, and mostly we're talking about the center of mass degree of freedom of those systems in the quantum regime. So starting from demonstrations of the quantum ground state, of quantum squeeze states of motion, non-Gaussian quantum states, and eventually quantum entanglement, not only between light and mechanics, such as Schrödinger originally envisioned it, but also between two mechanical systems. Now, this has been a development over the last, 20 years. And whenever we were working on that, the one thing that always, stuck in my mind a little bit, this was this aspect mass. In a way, you can view that as now adding another, let's say, quantum system, or another physical system to the zoology of controlled quantum systems. But there's something special to those mechanical systems. And it's not only that you can functionalize them, that you can put magnets on top, charges on top, and so on, and then use it as transduction system to other, let's say, quantum systems. But it is the fact that you now have control over mass. And this has been something I was always have been fascinated by. And if you look at that, so just as an example, I put here mass, so the mass of the system under scrutiny, and here the examples. And in all of those examples here, these are demonstrations of genuinely non-classical states of motion. So where the center of mass, degree of freedom, is essentially delocalized into a non-classical state. And you see that where the mass becomes large, so we start from single atoms, the half-meter superposition, the macromolecules. You also know the beautiful experiments by my colleague Markus Aspelmeyer in Vienna. And this is now here the regime, the high mass regime of quantum optomechanics, where we can reach solid state densities. Here's a little trait. Funnily, if you look at the amount of delocalization that you have in those experiments, you see it goes the other way around. So large mass means very small delocalization. So you can have in bulk acoustic resonators a collective motion of 10 to the 17 atoms, but the amount of delocalization is tiny on the atometer scale. Still, you get experimental signatures that you do have superpositions or delocalizations of these states, okay? And on the other end of this regime, you see you have the single atoms on the essentially meter scale or half meter scale that you can delocalize. And a fun observation here is now that the product of mass and delocalization is essentially constant. We are up to 2 or 3 orders of magnitude, but given that we spread here out by 17, 18 orders of magnitude, the fact that in all these experiments, the mass times delocalization product is essentially constant is very fascinating. I come back to that later. So again, what has been driving our research has been this question that always came up early on in these quantum optomechanics studies. Can we use this unique feature that we now can control solids in the quantum regime to have quantum experiments in which the gravitational field of the quantum system itself starts to play a role? So this has been the topic of our research since more than 10 years now. And as you will see, well, it's still a long way to go. Okay, so this is the question. What about quantum systems as sources of gravity? And in order to answer that, essentially you need to have three you need to provide three answers, right? So number one, how small can we make a source mass in gravity experiments? Number two, how massive can we make a quantum system? And number three, how do we verify quantum coherence once we have a large mass somehow allegedly in some sort of quantum state? Which brings me now to the first part of my talk title, the why. Okay, and since I'm sure there will be many other talks about that, and since my focus is more on the experiment side, here's my one slide why. Because all experiments that we have to date can be explained by assuming the joint validity of quantum theory on the one hand, and general relativity is our best theory of gravity on the other hand. So there is no reason to assume that gravity behaves according to quantum theory. Simply, we don't need it in the current experiments. And the examples that I give here are both well known. I just briefly mentioned it. Here's the beautiful experiment by Colella, Overhauser, and Werner, also the cow experiment after the initials of the authors, that show the influence of Earth's gravitational field on the wave packet of a neutron. So in essence, what happens is when a neutron traverses through an external classical gravitational field, it picks up a dynamical phase. We don't see global phases, but we see phase differences. So we send the neutron through an interferometer. We split up the wave packet into the two branches of our superposition in such a way that each of the two branches goes through a different height in the gravitational potential, and thereby picking up a phase difference. And now if you start to rotate the interferometer, you change the height difference in the gravitational potential, and therefore you get gravitational induced interference fringes, as you see here in this plot. Another example comes originally, so it's basically gravitational time dilation. And here's a beautiful example from the group of Dave Vineland, where they observe the change in frequency of the optical clock that is on this table when they lift the table just by 30 centimeters. And if you look in the current literature, here the groups of Genyi and other works, they are now sensitive to a height difference in the gravitational field on the order of sub-millimeter that they can see in their experiment. So it is fair to say that quantum systems are extremely sensitive probes of the gravitational field, however, of the classical gravitational background field in quantum experiments. And the problem that we essentially have now is, even though we do have quantum theories of gravity to some extent, we don't know whether we need those quantum theories of gravity. And these questions go back to I think most famously, the 1957 Chapel Hill Conference, where Austrian physicist Thomas Gold stood up and asked, I think, really the essential question. So can we have, given all of that, can we have phenomena which the classical theory of gravity is unable to explain? And well, of course, since Feynman was at this conference, he gave the inimitable answer, as always, Feynman-like, yes. And Feynman came up with the following Gedanken experiment that we have all heard of already. Basically, assume that you have some massive object in this mass and some type of Stern-Gerlach device that allows you to place this mass here and a superposition of up and down. Okay, this is this part here. And then assume that there's a second mass that gravitationally couples to this source mass in a superposition. What happens through gravitational interaction is, of course, that the two systems become entangled. And this, of course, from a quantum perspective is not a surprise at all. However, if you view it from a GR perspective, which is a classical field theory, this is, of course, a huge surprise, because your classical field theory actually tells you that no matter which source mass configuration you have on that side, the space-time metric that you generate is always well-defined, which means that a test mass which follows a geodesic in this well-defined space-time metric will never ever become entangled with the source mass when you start in a separable state from the beginning. And this is the fundamental problem, and this is why the generation of entanglement via gravity is a prime example for an experiment that cannot be described anymore by our existing classical field theory of gravity. Now, Louis Witten, he is the father of Ed Witten, was also at the conference, and he asked, of course, the most relevant question, namely, what prevents this from becoming a practical experiment? Well, if you look in the literature, we know there are many proposals how to do that. There's, of course, there are the famous BMV proposals here on the right side, and there are many other proposals, including also a lesser-known Perez paper from 2005 using BEC as the entangling source. And you can do so you can think of different configurations how you actually generate entanglement via gravity. So either you do it the BMV style, where your two masses initially separable are in two superposition states where the center of mass is in each case in a distinct, macroscopically distinct state. And then via the dynamical phase that we know already from the cow experiment, they actually become entangled. So this maps beautifully on a so-called conditional sign gate, which generates then entanglement if your target qubit and your initial qubit actually are both in superposition. The other possibility that you have is that both masses are in two Gaussian quantum harmonic oscillator states, also separated by a certain distance, and here the delocalization is essentially the full width maximum of the wave packet, and gravitational interaction then generates also entanglement. In that case, you know, the interaction is a 1/r Hamiltonian, and if you Taylor expand it, the first non-trivial part for an entangling interaction is the XX interaction, with in two-mode quantum optics is also known as a squeezing Hamiltonian. So starting off from the ground state, you then generate an EPR state. Funnily enough, for both of these cases, the rate at which you generate entanglement is the same. So it's given by Newton's constant over Planck's constant, mass squared, because it's gravitational coupling, delocalization squared is essentially the drive amplitudes, and 1/d cubed, because this is the first non-trivial part of the Taylor expansion. And this rate needs to be larger than the decoherence rates in the system in order to generate entanglement. Now, you may ask now, okay, well, so how long does it take to generate entanglement? Let me just give you two very quick examples. If I take two atoms that are separated by a micron and are delocalized by 100 nanometers, it would take 10 to the 24 seconds, which is 1,000,000 times longer than the lifetime of the universe to become entangled. If, in contrast, you take two large spheres, massive spheres, with 10 to the 18 atoms each, so like Planck mass scale objects, also with a few nanometer delocalization and separated by 100 microns, you see that suddenly you are in a 10 millisecond scale, which tells you increasing the mass and at high densities, because you need to keep the separation small, will help you to generate entanglement. Now, let me rewrite the coherence rate in terms of coherence time. And then basically, we have a wonderful expression, which is sort of the necessary precondition to generate entanglement via gravity in this context, namely the product of mass square delocalization square times coherence time times 1 over d cubed needs to be larger than Planck's constant over Newton's constant. And the nice thing about this expression is that you can separate that now into a part that I can independently check in a quantum experiment. So I try to build now quantum experiments where I maximize this expression here, and in gravity experiments where I now build up experiments where I try to minimize the gravity experiments where I try to minimize the distance between masses in order to enhance the gravitational coupling. Okay, so before I show you some stuff off from the lab, let me give you 3 additional experimental constraints that certainly are discussed in other papers in the literature, but I just would like to summarize a little bit my viewpoint on these things here. So number 1, a big problem with long coherence times and with, in general, the fact that we are now trapping large masses is the sensitivity to displacement noise. So just give you one example. If I have a particle, an atom in an optical trap, I pull it to the ground state, I prepare a pure state wave packet, typically the extension is on the order of 100 nanometer. If I do that for a particle with 10 to the 9 atoms, I go down to a picometer with my wave packet size. So if in an optics lab I have atoms, I have a 100 nanometer wave packet, and my lab shakes by, let's say, a nanometer, then it doesn't matter because my wave packet size is so large. However, if I now have a wave packet of a picometer and I still shake by a nanometer, then all hell breaks loose. I heat and so on, and I have huge problems. Now, this is why what I would like to do is I would like to work in an environment where I minimize my displacement noise. And one way to actually achieve that is to go to short timescales. Short timescales means larger frequencies that I'm sensitive to, which means since displacement noise scales with 1 over omega square, where omega is the relevant frequency, which means that I really want to put a bound on the duration of my experiment. And just out of experience, typical rates, so typical frequencies below which life becomes more easy is the 100 Hertz scale. So I just now define the duration of my experiment to be smaller than 10 milliseconds. Okay, so I'm bounding coherence time. Now, another challenge is now gravity experiments. If I want to be sensitive to gravity between two masses, I need some electromagnetic shielding between the masses. I have not yet seen, let's say, a convincing way how to avoid any sort of electromagnetic shielding between the masses. The current world record is 50 micrometer between the two surfaces. And this is actually done by a, you see, gold-coated beryllium copper membrane in that case. And what we are doing now, we have been teaming up with Eric Adelberger from the famous Earthwash group, and we are now actually trying to do an experiment on the order of 10 micrometers. So we want to decrease the distance down to a level of 10 micrometers. So this is our second working assumption is we need a Faraday shield, and the surface distance will be on the order of 10 micrometer or a little bit above. So we are bounding from below the possible distance between the two surfaces. And by the way, since we're talking about quantum origins of gravity, at the same time, a gravity experiment at those small distances is also related to tests of large extra dimensions, which are in a way also related to some quantum gravity aspects, because, for example, string theory predicts some possible observable influences of such large extra dimensions. Now, the last point is, once we are in a superposition above a Faraday shield, there will be decoherence. If this is not a perfect conductor, any sort of absorption will lead to leak of which location information in our shield, and this decoherence will somehow scale with some order of delta x over d. So the last requirement that we have is that the delta x over d should be much, much smaller than 1, okay? And so if I now put all of that together, what I just shown you is we bound with these 3 boundary conditions. We are bounding the delocalization, we are bounding d, and we are bounding the coherence time. And this now provides a bound for the mass. So if I put all of these 3 conditions together, it shows you that the mass in such an experiment, in order to fulfill our initial condition, has to be much larger than 10 to the minus 6 times the Planck mass. And all of that in a volume of d to the cubed, where d was the 10 micrometer, and then you see immediately that this requires solid state density. So for such an experiment, you need a solid in order to generate entanglement via gravity. So let me just show you. If you now think more about decoherence, if you add now blackbody radiation, if you add now gas scattering of background gas, which is, by the way, another reason why you want to keep your experimental time small, you end up in a table. Don't worry, I will walk you through it. So basically, the boundary condition is 10 milliseconds coherence time, fundamental distance of 10 micron at the most, at a minimum, and solid state densities on the order of 10 to the 4. And now let me just show you this example. It would mean that if I have a Planck mass, 10 to the minus 3 times the Planck mass, so 10 to the 15 atoms, that's like approximately 8 micron sized object, and a delocalization on the order of 100 nanometer, and temperatures of the environment and the object itself on the order of 10 Kelvin, then we can generate entanglement on the 10 millisecond scale. And so this is our benchmark. So the question that I'm asking now for the remainder of the talk is something like that in principle feasible? So reality check. Where are we with respect to quantum systems as gravitational sources? And let's focus first on gravity. So when we asked this question some years ago, basically the smallest source mass in a tabletop experiment on Earth was on the order of a gram. And we wanted to somehow get into the game, and we said, okay, let's see if we can improve that by an order of magnitude and learn what it takes to measure gravity very precisely and be sensitive to gravity on small scale. So what we did was we essentially built a microscopic version of a Cavendish experiment where you have a torsional balance with 2 millimeter scale gold spheres on a glass rod. You see this can rotate. It's a torsional pendulum, and you have a source mass with an amplitude modulation here of a few millimeter. The distance between the surfaces was on the order of a few hundred microns, such that upon modulation of the source mass, the acceleration modulation at the location of the test mass here was on the order of 10 to the minus 10 meter per second square, or 10 to the minus 11 G. And this actually translates, given the properties of the torsional pendulum, of a displacement on the nanometer level. Now, reading out displacements on nanometer level is a piece of cake. However, obviously, you need to put your pendulum in your lab, and there it should also be stable on the nanometer level or below in order to discriminate the gravitational signal from all the other signals. And what you see here is a frequency versus time plot, where this is just the response of the pendulum in the lab without any additional source mass present. And you see the yellow is a lot. So you see at the 10 millihertz frequency, there's a huge response of our pendulum. And why? Because 10 millihertz is the traffic light cycle of a road crossing 100 meters away from our lab. So when these two streets, Nussdorf and Währinger Street, actually cross each other, trams stop and accelerate, buses stop, accelerate, pedestrians stop, and so on and so on. And there are higher orders of that. And you see there are like these dark stripes, and the dark stripes is where nothing happens. And this is when the trams stop operating. So this is between midnight and 5 a.m. This is our measurement slots. And you see you always have 1, 2, 3, 4, 5 dark stripes, and then 2 less dark stripes. And this is Friday and Saturday night where people are simply out on the streets. Okay, so this gives you now, this gives you the times where you can measure. And then what you do on top of that, you also make use of the fact that during Christmas, people stay more at home than usual. And so what we came up with then here is this beautiful result where you see here, this is the gravitational response of our pendulum test mass following the drive of our 90 milligram source mass. You also see a higher order here. The higher order comes from the fact that what we are modulating is a 1/r potential. So it's a non-linear modulation. And this is why you also get higher order responses from the pendulum. And I should also note that the precision with which we measured this acceleration was on the order of 10 to the minus 12 meter per second square, or 10 to the minus 13 G. So where does this take us? Well, the next step, what we want to do is, instead of having this as the source mass, we actually want to have a small mass here of that size on the order of 100 microns, which is essentially Planck mass source mass. Now, we cannot do that anymore in our lab in the city in Vienna, so we're going underground. This is actually Hans building up the experiment as we speak in this beautiful tunnel system. The experimental conditions, they are incredible. You see seismic noise. These are real-time time traces. Instead of changing by many orders of magnitude during the day, you see nothing changes at all. The only thing that changes here, you see this red one here, this was an earthquake hundreds of kilometers away, and you can see the earthquake actually, you see, rung up our experiment. But the nice thing is we have independent sensors there, so these are things we can veto during the course of our experiment. Here is a picture of our Planck mass object. So this is a small silicon cylinder that sits on top of this disk. There are 5 of them, and they are rotating now in front of our test mass pendulum that will then be again accelerated, and that should measure now the effect of a Planck mass as a gravitational source. So to wrap up our gravity experiments, so basically now we showed that we can go down here now to around 100 milligram, and we should, again, as we speak, we are measuring, we should see a signal of a Planck mass gravitational source very soon. So, which brings me to my last part, the question, what about the quantum systems? Remember, this is the number we need to make large. So we need to get mass large, delocalization large, coherence time large. And where do we stand at the moment? Well, there are these 2 extremes, right? On the one hand, we have the macromolecule interference experiments, which are beautiful, by my colleague Markus Aspelmeyer here in Vienna, where we have on the order of 10 to the 3 atoms delocalized over enormous amounts, right? 500 nanometers. On the other hand, we have the solid state systems. I already gave you a glimpse of how these things work. This is a beautiful example where actually you see this aluminum nitride slab here was capacitively coupled to a superconducting qubit. So you could directly now, through the qubit nonlinearities, you could generate non-classical states and superpositions, for example, of energy eigenstates of the thickness oscillations of this aluminum nitride plate, which means you now have collective motion of 10 to the 13 atoms, so 10 orders of magnitude larger than up here, however, with a delocalization of only sub-femtometer. Now, if I put that in numbers, in hypothetical numbers, where we say, oh, I now compute mass times delocalization and the square root of coherence time in units of h bar over g at a hypothetical distance of 10 micron, then in order for the system to be capable in principle of generating entanglement by gravity, this should be on the order of 1. And as you see, they are still far away from that. So the recent beautiful works by Yi and Zhu at ETH with the bulk acoustic modes see again 7 orders of magnitude with respect to the Cleland results here, but it's basically still playing in the same ballpark than the macromolecule. So we are basically lacking 20 orders of magnitude still. So the question that we have been asking was, how can we sort of use the mass of large oscillators and break this vicious circle of the delocalization becoming smaller and smaller when you crank up the mass? And the idea that came up was, well, use levitation. Okay, namely use the solid state system, the advantage of the solid state system, combine it with the advantage of AMO systems, and put it together in such a way that I now levitate a solid in an externally controllable potential landscape. Because that means I can, for example, take an harmonic potential as my trap to do ground state cooling, so I can actually prepare my wave packet in a pure state. Then I can switch off the trap, for example, and in free fall delocalize the wave packet by many orders of magnitude. So for example, only after 10 milliseconds, you see, I actually would have something like 40 dB in squeezing, and my delocalization would already be on the order of the particle radius. There have been beautiful ideas, in particular from the group of Oriol Romero Izard, how to use then, for example, an inverted potential to speed up that even more. So I think there's a lot of wiggle room here to continue. So where are we with respect to levitated systems? Just to mention, optical levitation is an old hat, so to speak. So Ashkin pioneered that in the 1970s. And by 1985, the group of Ashkin, together with Steve Chu, had developed the ideas of an optical dipole trap where they would be able to both trap atoms on the one hand and a nanoparticle, because they both basically behave in a similar way with respect to their polarizability if you have if you're sufficiently detuned from the atomic resonance. So this is what we are doing in our experiment. We have a nanoparticle that sits here in the strong focus of a microscope objective. The idea is it's a dielectric particle, so that the potential landscape that the particle sees is essentially d dot E, so the dipole moment times the electric field. The dipole moment of the particle is, of course, the applied electric field times the polarizability. So that means in the end, what you get is simply a potential landscape that is proportional to the intensity of your laser beam. So that means if I now have a focused laser beam, I have a Gaussian intensity beam profile. And the potential landscape that I see is just the negative of that. So you see now that for small displacements, you are essentially only seeing an harmonic potential. And all of that is true in all three directions, because you have 2 times Gaussian and 1 times Lorentzian profile, which in all 3 cases gives you a nice 3D now harmonic confinement of the particle. Now you put that whole thing in a vacuum chamber, you see here, then the forward scattering is used to collect X, Y, Z information of the motion, which you can feed back now to the particle trap to stabilize the position of the particle and can go into ultra-high vacuum. Just for the experimentalists, because this is so much fun, the way how we get particles in without contaminating the chamber, because the way we're actually preparing the particles in an aqueous solution, and in the solution we just spray it in a chamber, but this would contaminate the UHV chamber. So we're connecting now a bad vacuum chamber with our science vacuum chamber at ultra high vacuum using a photonic crystal hollow core fiber. We have 2 laser beams such that we get a standing wave trap. Such that when we now can load a particle in front of the, in the standing wave here, we just detune the frequency difference, and then we have an optical conveyor belt that is pushing the particle to the high vacuum chamber. And you can see that here, you see that now, you see zoop, the particle, yep, I hope you can see it, the particle is going through. Let's see one more time. You see there's the particle, zoop, and it goes to the science chamber. Once the particle is in the science chamber, you hand it over to another trap, you put a cavity around it, and you play the same tricks that I just showed you for cavity optomechanics. Namely, you detune now your tweezer frequency that is responsible for the scattering with respect to the cavity frequency, such that the cavity becomes resonant only to the anti-Stokes scattered light that takes away energy from the center of mass motion. And this allows you now to ground state cool this particle motion into the quantum ground state, starting from room temperature. So this is something that we did in cooperation with Vladan Vuletic some time ago. And only recently, this has also been demonstrated in 2D. And just as a side note, it was a very fun fact. You see, the first paper ever on trapping a solid-state particle by Ashkin was January 1970, and essentially almost to the day, 50 years later, was our paper on cooling such a particle to its quantum ground state. Okay, so I wrap up. Let me give you a little bit of an outlook here. Cavities always have an issue with technological overhead. So we were asking, can we also do it without a cavity? And so what we have developed now is basically a Heisenberg microscope, where this is the experiment that I showed you before, with the addition that now we actually look also at the backscattered light, and we use methods from biology, actually, so confocal backplane imaging, which is a super low noise method of detecting the backscattered light. And we can do that in such a way that the back action imprecision product is very close to h bar, which means we have built a Heisenberg microscope. And if we now take the information that we have, which is basically only limited by quantum noise now in the system, we can use a Kalman filter, which basically means a stochastic Schrödinger equation to process the data in real time, make a prediction of the particle position in phase space, use new data to update and verify that information, and such in a Bayesian manner have a real-time reconstruction of the quantum dynamics of the particle in phase space. And then once you have that, you can, of course, also use it to feedback on the particle to stabilize its position in phase space with a precision given only by the ground state uncertainty, which means you laser cool the particle now into its quantum ground state of motion, or feedback cool it. So here's the trajectory in phase space, and then we localize it here in the center, and we verify in an out-of-loop measurement that our particle is in its quantum ground state. Here you see a picture of the particle while it's in a room temperature vacuum chamber and cooled to its quantum ground state of motion. So this is a ground state cooled particle where we have prepared now a pure state wave packet. Okay, the future. And I think this is now the big question that we have to answer. So we know how to prepare pure state wave packets of massive objects in a levitation setup, which is good because this now should allow us to really delocalize very, very, very strongly. Okay. And so we have been looking at ideas in the past. So together with Oriol Romero Izard, we actually already back in 2011 had some suggestions how to use projective measurements in cavities to generate such states in post-selection. You will hear in the next talk by Ron, there's some beautiful ideas using essentially techniques from AMO physics. We have an internal degree of freedom and state-dependent forces to generate superposition states. Or one thing that we are following now is actually use the fact that we have traps and that we can have coherent dynamics in the trap. So one thing, we call it the Super Mario protocol, is, I don't give you much of the details, but the point is, you see here the potential landscape is dynamical in time. We start with an harmonic potential for ground state cooling. We switch off the potential such that we get free evolution and large delocalization. And that is already basically most of the story. And then what you can do in order to verify that you now have strong coherence and coherently delocalized state is you apply now a cubic intensity pulse, which provides a phase modulation on your wave packets. So essentially it's a phase grating with a period that is much, much smaller than the optical wavelength, because it only depends on the intensity gradient that then generates interference fringes. Now you may ask, okay, well, but will this get the 20 orders of magnitude that we wanted? Well, it doesn't, because we are still talking about nanoparticles here. But you see, we already advanced by almost 10 orders of magnitude. Where do the remaining 10 orders of magnitude come from? Well, from the mass. So we need to go to larger masses. We need to go away from 10 to the 9 atoms. We need to go to more atoms. And here's an example, an experiment that we're currently doing with 10 to the 18 atoms. So it's a Planck mass object. It's a superconductor that is levitated in the anti-Helmholtz coil configuration inside a dilution refrigerator. It's diamagnetic levitation in an ultra-cold environment. We read out the motion via a squid. And basically, we hope that we can also reach there a Heisenberg limited measurement, which would allow us to ground state cool and hence prepare pure state wave packets. So this is work in progress. Another work in progress is that we look at the interaction between two particles. And basically, we have recently shown, this was the work of Uroš Delić, that coherent scattering leads to light-induced interactions. You can switch those interactions off by changing the polarization to orthogonal of the two particles in the two independent tweezers, and that results then in Coulomb-driven coupling between the two particles. And now we're trying to see whether we can generate entanglement via Coulomb interaction between these particles. Okay, so I will stop now. Let me just conclude with a couple of summarizing statements. So number one, the question that we have been looking in and are looking in is, what if we could have quantum sources of gravity in the lab? And what we need for that is really, we need quantum states that can be gravitationally distinct, which means there has to be some gravitational experiment through some observer that distinguishes these two quantum states, because this is equivalent to saying that we then can generate entanglement in the lab. And this distinction needs to be through gravitational measurements. You can, of course, ask the question, well, why go through all the hassle of having masses and Faraday shields and so on? Why don't you just put a clock there? Right? Because we know that clocks are super and use gravitational time dilation. And you can do that. But actually, if you do a back-on-the-envelope calculation, assuming what I just said here, that you get like a Planck mass object with a couple of nanometer of delocalization, the typical frequency difference that your clock would be able to resolve in order to generate entanglement would be on the order of 10 to the minus 32. If you compare it with current clock experiments, we are still off 10 orders of magnitude. So again, this might be another possible way. We just need to improve experiments further. Okay, so final statement. Since I'm coming from the field of quantum optics, you know, Bell's theorem is a big thing. And so one possible way of formulating the fundamental incompatibility that is at stake when we talk about entanglement by gravity, you can do it in a sort of an incompatibility theorem. And if you want to do that, then one way to phrase it is that at least one of the following statements is not true. Number one, all gravitational phenomena are classical. Number two, gravitational interaction is mediated by gravitational field. Number three, gravitational interaction can generate quantum entanglement between two masses. The third one, we can experimentally test. So if this is a yes, then there has to be a no to at least one of those two assumptions, or to both of them. So with that, I hope that I could show you where we are right now in our attempts to increase mass in quantum experiments on the one hand, decrease mass and distance in gravity experiments on the other hand, and hopefully at some point go into a regime where we can start probing gravitational phenomena of masses in quantum states of motion. So with that goes a big thanks to my team, and a big thanks to you.
Thank you for this great overview. We have time for one quick question, unfortunately, either from here or from Zoom.
Hi, Professor Aspelmeyer. I wanted to ask that you said that the density needs to be like 10 power 4 kg per meter cube, right? And we know, like, for diamonds, which are proposed for these kinds of experiments, the density is lower than that. So would that mean, like, diamonds incompatible with the experiment?
No. So the numbers that I showed were numbers using the assumption that I have a density of 10 to the 4. Okay, but honestly, it's not a big thing, because density really only enters quadratically. So if you are a factor of 2 or so away, you know, you just have a factor of 4. So this is basically density-wise, it's not a big issue. No, you just adapt the other numbers a little bit.
Okay, thank you.
But that was a good spot. Yes, thanks.
Okay, unfortunately, we have to continue with the next speaker. Thank you very much.
Thanks.
Okay.